A very good morning to all of you and welcome to today's session. And before we start, I will just uh, take 1 or 2 minutes to share my slides and tell you about K-fold cross-validation, which we'll be using. So that we didn't have time yesterday. So just allow me. And after that, we will start with the hands-on session. So just allow me a minute. I will share my slides and go on from there. So I hope all of you are able to see. Yeah. So actually, in the previous lectures, I've told you about how to split train and the given data set into train and test samples. And for that, we had actually done a graph of the performance of the model versus the split ratio. And we try to vary the split from 60, 40, 70, 30, 80, 20, 90, 10 like that. And we, after looking at the performance, we decided to choose one particular split, which is actually the 80-20 kind of a split for further model building and analysis. Now, that was one way of splitting the given data into train and test. There's another way to do it, which is called K-fold cross-validation. So, K-cross-fold validation involves uh, actually breaking or dividing the given data into folds. What are folds? Folds are nothing but disjoint subsets. So, what we do is that we have the input data, and in this case, K is the number of subsets or disjoint sets in which we are going to, or folds, in which we are going to divide the given data. Okay. So don't confuse this K with the K nearest neighbor, where in K nearest neighbor, K is a number of neighbors that we are considering. When we talk about K-fold cross-validation, we are actually talking about K subsets which are disjoint. They are also called folds. So the given data set is actually divided into these subsets, K number of subsets. For example, if K is equal to 5, you can see in the diagram, 5 folds will be formed with 20% data in each fold. Out of these, one fold will be kept for testing as the test data, and rest of the 4 folds will be used for training purpose to build the model. And the ML model will actually choose different subsets as the test set, so that there is no bias that is created because of certain data falling in some particular subset. So for example, what you are seeing here are the 5 folds. In the first iteration, the fold 5 is chosen as the test set, and the rest of the 4 folds are chosen to do the learning and as the training data to build the model. Then in the second iteration, the test set is moved, is now fold 4, and the rest of the data is the training set. Similarly, in the different iterations, the different folds are used as the test set, so that there is no data bias and the complete variability of the data is available in the training and the test set. And the final performance of the model is given as the average performance of each of these models. So when we choose the first fold, second, third, fourth, and fifth like that, and the rest of it as training data and one fold as the test data. So for each of this, we build the model, find out the performance. Let's say the performance matrix gives values given by performance 1 in the first iteration, and so forth till performance 5. Then we average out, and then the average gives the final performance of the model. So like this, in this particular case, we have another method which is called K-fold cross-validation, which is used to divide the given data set into train and test sets. And here no other split is required like we used to do earlier, 60-40, 80-20 or 90-10 and all. Nothing is required. Only folds are to be formed. Folds are nothing but subsets. They are disjoint with respect to each other. And one of them is kept for test purpose. The other is kept for training. And like this, the model works. So is it okay? Any questions on K-fold cross-validation? Anyone?
Ma'am, final model, which one we will use to predict maybe unseen data?
So the final model actually, uh, so what is happening is that your final model will be the average of all these. So in the final model, whatever model you are having, you will decide some value of k, and for that many folds will be created, and so many iterations will happen, and your final model will be giving you the average performance. So actually your final model is nothing but it's made up of so many sub models actually. Is it okay? So your final model is not a single model. The number of folds you decide, it will go through those many number of iterations, your model. And then finally, it will give you the overall performance, which will be actually the average on all these iterations made out of so many folds. So
Okay,
actually, in a way, it's not a single model, it's the average of different models.
okay, okay.
Yeah. But when you actually use a Python code, the function in itself does all this. So we don't explicitly code this. We just
Okay,
choose a value of k, and then we use it and give it as a hyperparameter, which you will see shortly in the hands-on session. And automatically, internally, all this will be done.
okay, okay.
Yeah.
Ma'am,
Any other
Shashank this
question?
right? Yeah.
Yes, Shashank.
Ma'am, when we are making 5 iterations, right? Suppose in one of
Mhm.
the iterations the values are not coming because of the sample distribution. So do we also take feedback and improve our model in between?
So the standard k-fold cross-validation doesn't have any input here. All it does is that it divides the data into disjoint folds or subsets and uses, iterates upon the test sample as one of the folds. So there is no implicit feedback here. If you wish to do that, then you'll have to explicitly create some mechanism to give the feedback. Okay.
Yeah, got it. Okay.
Okay.
I'm Muthu here. I have a
Mm-hmm.
question.
Yes.
For this, is there any constraint of k cross fold validation can't be used for any models, or it can be used for any models?
It can be used for any model. We are talking about supervised learning and classification models. It can be used on any model. So it is only a way to actually divide the given data into train and test, and that's all. So that we have to do for any classification model. So there are two ways. One, you do the split yourself and observe the performance and choose the correct split ratio, or
Mhm.
you have a this method, and that's all. Yeah.
Got it, ma'am. I'm sorry if I missed. How do we choose the k value here?
Yeah. So the K value you will just see in the hands-on session. So you will actually have to draw a graph of the performance of the model versus different K values, and then choose the optimally best K value. I'll show you in the hands-on. We'll just discuss.
Sure, sure, ma'am. Thank you.
Yeah, Vipul, you have raised a hand.
Yeah, ma'am, you said that all the folds which we have in the data set should be, you said they should be disjoint. But how we will
Yes.
create those folds so that there should be no overlap, and so our test data should be different for each fold. Just wanted to uh, just have that query on that.
Yeah, so actually, folds are nothing but partitions. So you just take, let's say you've got some 100 samples, for example, and you need to have 5 folds. Then you are going to keep 20 records in each fold. And that's how all of them will be disjoint. There's also something called stratified, K-cross folding, in which let's say you are choosing 5 folds, so 20% data is going in each fold. Then that 20% will contain the samples in a ratio which is pro rata. That is, if there are, let's say, 2 classes and there are certain amount of samples belonging to one particular class and some samples are from the other class, then in the same ratio that 20% will be populated. So, so there's nothing much. You are only required actually in the k-fold cross validation function that you're going to choose. This happens. This is already pre-coded, so you don't have to do it explicitly. But if you have to code it, then you have to just divide the data into the number of subsets that is specified by the value of k, in such a way that they are all disjoint and there is no overlap. So that's all we do.
Yeah, so you said in k-fold function is already pre-coded. So do we have a kind of formula ki acha, if the 100 samples are there, then it will be it will be divided into 5, and so there will be same kind of number of elements will be there in each fold. So that logic is there already in the function.
So I believe your question is what should be the value of k? Is that what you wanted to ask?
Yeah, yeah.
Yeah, so you will just see in the hands-on session how to choose an appropriate value of k, for which you will actually have to iterate upon different values of k, and you will have to draw, actually have to analyze the performance of the model versus the k value, and then choose an optimally best value where the performance is good. This is how you do it.
Yeah, got it.
Okay, Meghna, you have a question?
Yes, ma'am. So, is there a consideration or scenario in which we go ahead with a manual test train split or a k-cross fold validation? Or we
Both
can.
these methods, you can do any one. Both
Okay.
are actually equally popular, and pretty much the results of these might be parallel only, because in both these you are actually deciding how much data. Let's say you have this 5 folds and you keep one fold and keep the rest of the data. Anyway, you are doing 80-20 split only. So more or less they are similar, but the way to achieve is different.
Okay. And we can also do a test train split plus validation also in certain type of data, right? Like when we are implementing a model.
What you are saying is that you do a split, like 80-20 split, and then do a k-fold cross validation.
Maybe like 80% data, 10% goes for test, 10% goes for k-cross validation. Like that also we can do. Is that like possible, or maybe like guidance you can say?
Yeah, so actually, because these both are achieving, they are both designed to achieve the same goal. So therefore, they are parallel methods. You can do one of them. So usually I haven't come across a case where you would be doing a split and also doing a k-fold, because a split is doing the same thing what k-fold cross validation is doing, because one fold will be used for test, rest will be used for training. So depending on the number of folds, you are actually also splitting only the given data into train and test. So it is advisable to use one of these two parallel approaches to divide the given data into train and test data, and that. So both of them are usually not used together.
Got it. Thank you.
Okay, any other questions? Okay,
Ma'am,
so I
can
think,
you sorry, ma'am. Ma'am, can
yeah,
you
go
provide
ahead.
more insights on how to create fold, ma'am? Because when we get a data, how to categorize it such that it will be exclusive?
What you want to say is that how to form disjoint sets, right?
Yes, ma'am. Yes.
Yeah, so actually, if you use a pre-coded k-fold cross-validation function, then you don't have to form the folds yourself. The system will do it. All you have to choose is the k value. That's all you have to do. But in case you want to form the folds yourself, then depending on the value of k, what I would suggest is pick up stratified samples. So what are stratified samples? Stratified samples means that the number of samples picked up in any fold will be in proportion to the total number of samples belonging to all the classes. Let's say there are two classes, C1 and C2, and they are available in certain ratio, let's say 75-25%. So 75% records belong to class C1 and 25% belong to class C2. So if that is the case, then stratified folds mean that each of the folds will have this kind of distribution maintained in it, that each subset will still have 75-25, 75-25 like that samples belonging to class C1 and C2 respectively, like that. So that is how the samples are done. Other than that, they are all disjoint. So there's nothing more in it. Only you need to, it is advisable that you ensure that it's not mandatory, but it's a good idea to have the samples in a stratified fashion. And as I told you, stratified means the proportion of the different classes is maintained in the subset or the folds also.
Got it. Thank you, ma'am.
Yeah. Thanks. So I think now I hope all of you been able to load the files so that we can start with the discussion and you are not lost loading the files. Are you all ready? Shall we start, or shall I give you a minute to load? So what I'll do is I'll request Ashish. We are having Ashish here. Ashish, can you please turn on your video? Welcome Ashish to the session. And I'll request you to share the Python code, and we'll have a walkthrough on the overall flow in the code, and then Ashish will take you through the detailed steps. In the meantime, while I'm taking you through, if those people who have not loaded the files, please do so. I hope anyway all of you must have done it already. So now in today's code, we are going to actually try our hands on what we learned yesterday. So yesterday we learned about k-nearest neighbor, we learned about naive-based classification, and I also discussed k-fold cross-validation, which is a parallel approach to do train test splitting. So now for today, to try all this, we have chosen another data set, which is the adult census income data set. Which is there as part of the UCI dataset repository, or it's also available. So we have taken it from there. And this particular data set has the classifying attribute as the income. So income more than $50,000 or less than $50,000. So greater than equal to is one class and less than 50K is another class. So it's a binary class problem, and given the different attribute values, which are the features over the individuals which are represented in the data, we have to predict whether the person will be having income greater than equal to 50K or less than 50K. Ashish, I'll request you to enlarge slightly so for better view. So the different attributes that are available, you can see there. These are a combination of categorical attributes as well as numeric attributes. A slightly larger, Ashish, a little more will be helpful. So the different attributes that are there are like age, working class, education level, and so on and so forth. And you can see the data types also alongside. Then if you'll just scroll down. So then there are different Python packages that details of which Ashish will walk you through. I'll just tell you about the flow overall. So you can just please go down, Ashish. So first step obviously is in any Python coding is to load the data frame. So this is after loading the data frame, the top 15 records are just shown. You can have a look. So different attributes like age, work class, education, marital status, then what is the occupation, relationship, etc., race, and then capital gain. All these kinds of information is given for each and every individual, which is represented on the data. Please go down. And there are approximately 32,000 records in this particular data set. And there are around 15 columns. And you can see the different data types, which is a mix of numeric and categorical data types. The integer values you can see here represent the numeric data type, and the object type is nothing but the categorical data type. So the next step is the standard step that we check for missing values. And you can see here that certain attributes like work class, occupation, and native country, these contain some missing values. So if we talk about 32,000 records, so these are not many. So in this particular case, and it's also difficult to fill them. So what we have done is, you can see here the percentage. So in the working class, around 5.64% is missing. Occupation again 6%, and native country 2%. So these are the values that are missing because they are not many. So for our purpose, we have just ignored those samples, or you can consider that we have just removed those samples from the data and considered the rest of the data for our further analysis. So now what you will see here is that the number of entries have reduced slightly because so many records have got dropped, and now we are having around 30,000. So around 2,000 something records have got dropped because of missing values. Okay, let's go ahead. So you can see that there are no missing values here. The NaN values are all 0. Okay. Now we know that in the data set there are two types of attributes or columns, one categorical and one numeric. We already have seen them. This is just a explicit analysis showing these two categories. Then we'll find out in the categorical attribute how many unique values are there. Remember, categorical attribute is one which is having a finite number of values in it, like yes, no, and so on and so forth. So we try to find out how many values are there. So for each of these, for example, in the working class, there are 7 unique values like working for state government, self-employed, private, federal government, local government, self-employed, and so and without pay means not working, and so on and so forth. So like this, there are different number of unique values for each of those categorical attributes. Ashish, you can scroll down. And then if we look at the target variable in this data set also, the target variable, which is the income, is quite unbalanced, with most of the people having income less than or equal to 50K. That is around 75% of the data falls in this category. And the rest of the 25% around falls in the other class, which is income greater than 50K. So maybe you can scroll down, Ashish. So this is the graph. Now we come to the model building part. So to build, let's start with k nearest neighbor. So to build a k nearest neighbor based model, the first thing is that we want to decide what should be the value of the number of folds, right? So because we need to build any model, we'll have to split the data into train and test. So in this case, we are going to try using k-fold cross-validation. And so here the k means the number of subsets we are going to form, or the number of folds. So what we have done is, by fixing the value of number of nearest neighbors to certain values, say 5, we have tried to see the performance. So you can come to the graph, Ashish, and then later you can explain the code when you take the detailed analysis. So what happens is that we try to look at the performance of the model. And for that, we have tried to vary the number of folds. I think this was a question which many of you had asked, that how do we just wait there you can just, yeah, you can keep it like this. So how do we decide the value of the number of folds? So the number of folds here, to decide the number of folds, we have tried to look at the performance. The performance of the model will be something like accuracy, precision, decall, F1 score and all. And these are plotted against the number of folds. So the number of folds that have been considered is a odd value, like varies from 3, 4, 5, 6, 7 like that. Okay. And then the different graphs. So the values that have been considered are from 3 to 7, as you can see here. And you can see 3.5, 4.5, and also this is just the tick size that was decided by the system. Actually, there's no need for anything like 3.5, 4.5 and all. All we have is 3, 4, 5, 6, and 7. So we try to look at the performance of the model, taking different folds, which you can see here on the x-axis, and then we choose the value that is optimally best. So you can see here that accuracy is for the train and test is quite good at k equal to 7. Similarly, the precision, decall, F1 score, and so on and so forth, most of these performance metrics come out to be good for k equal to 7. So the number of folds that we decide are 7 in this case, with k equal to 4 also giving slightly similar performance, but having more folds is better, because then you can get a better average on the different folds. So then we decided with the value of 7. Then we went ahead to form the k nearest neighbor based classifier. Remember that to decide the number of folds, we had fixed the number of neighbors to some value, that which was 5. Now we are going to vary this value so that we decide, we have fixed the number of folds to 11 and 7. And now we are going to see how many nearest neighbors to consider. For this purpose, we have considered the odd values. Why odd? Because sometimes we may need to take majority vote of the class classifying attribute or class label. So if we have 2, then it could be 50-50, falling having 1 class each. So to have a clear majority, odd numbers have been used, like 3, 5, 7, 9, and 11 and 13. Then to build a model, again, we have categorical and numeric attributes. Now, I told you last time that there are different ways to actually represent categorical data. One is using one-hot encoding, which we had used in the last hands-on session last Sunday. And I had also told you about integer encoding. So one-hot encoding is quite popular when the number of values inside any particular column are not too many. Integer encoding is more popular when the number of values inside, unique values inside any categorical attribute is large. So we are, in this particular case, we have used both one-hot encoding also and integer encoding also parallelly to see which one gives the best result. And for numeric attributes, we have normalized all the attributes using standard scalar. The reason for normalization we have discussed earlier also is as follows, that certain attributes will have very high range, let's say from 1 lakh to 20 lakhs, whereas some others may have very low range, say 10 to 100. So if we use all the attributes in their raw ranges, then what will happen is that particular attribute that has a higher range of values will dominate the distance. So all of them are brought to the same range of 0 to 1, and so we scale them. So this is what is done on the numeric data. You can scroll down, Ashish. So we'll first handle the categorical data. And to do that, we will use integer encoding. And then, so first of all, integer encoding has been done. Technically, in Python, this function is also called ordinal encoding. So therefore, the name ordinal encoding can be taken as synonymous to integer encoding. So you might see both at different places. Okay. So integer encoding has been done for the categorical columns. Please scroll down, Ashish. And after that, standard scalar, that is normalization, has been done on numeric values. And then we want to decide on the number of neighbors, that is k nearest neighbor, that value of k we want to decide. So to decide that, what we have done is plotted the performance of the models versus the value of the number of neighbors in k nearest neighbor. So as we discussed earlier, we'll vary the value from 3 to 13 and see where the model gives the best performance. So you can see here the optimally best performance where both training and test data give good performances somewhere like around 11. So 11 may be chosen to do the rest of the calculations. And before that, it may be underfitting, and beyond that may be case of overfitting. So you can scroll down, Ashish. So after deciding the number of neighbors, we'll now fit the model using categorical data, which has been one-hot encoded, and numeric data that has been normalized. And we'll now study the final performance with number of folds equal to 7, and the number of neighbors to be equal to 11. And these are the different performance values that we are getting for accuracy, precision, recall, and all. Now we will do the whole exercise again, but in this particular case, instead of integer encoding, we'll do one-hot encoding. The rest of the stuff remains the same. Here again, we'll iterate on the different values of k, that is the number of nearest neighbors, to decide which number of nearest neighbors to choose along with one-hot encoding. So there will be similar graphs that we have drawn earlier. And then again, we'll see in case of one-hot encoding, what will be the number of neighbors we must choose. The results are parallel to the previous case where we are doing integer encoding. So probably 11 may be chosen again. So now with k equal to 11, that is 11 number of nearest neighbor and 7 folds, we will build a model with one-hot encoding, and then look at the performance measures. And then we'll also do a comparative of both of these models, that is k nearest neighbor with one-hot encoding versus k nearest neighbors with integer encoding. And you can see here that though the performance is almost parallel, not very different, but one-hot encoding is slightly better. Now we are done with k nearest neighbor. Now we'll go to naive Bayes. So in naive Bayes, again, we need categorical attributes or discretized data, because it works on categories, the naive Bayes classifier. So categorical attributes, again, we have treated in two ways, that is one-hot encoding and integer encoding, and then done the model for both of these, whereas for the numeric values, discretization has been done. Okay, you can scroll down, Ashish. So then here the discretized values have been chosen. So you can see now the attributes, the numeric attributes have been discretized. For example, there was an attribute like age. So it is now discretized into bins like 2, 4. It is having discretized values like 2, 4, 2. So bin number 2 is assigned to it, and so on and so forth, like that. Now the data is ready. You can scroll down. So first we are doing integer encoding on the categorical attributes. For the numeric attributes, we have done discretization already. And after doing that, we will build the model and see the performance of the model using integer encoding, right? And the performance metrics have been shown here. Then the next part is doing, in addition to integer encoding, we do one hot encoding for all the categorical attributes and then use naive on it. And then we compare the naive with one hot encoding and the naive with integer encoding. You can come to that part, Ashish. So I'm telling you very broadly the overall flow, and then Ashish will take you through that. So you can see here, now we have compared k nearest neighbor in integer encoding, one hot encoding, and naive Bayes in integer encoding and one hot encoding. And you can see here that naive Bayes with one hot encoding and k nearest neighbor with integer encoding. These two are slightly working better, means one hot encoding may be better in this particular case rather than integer encoding. Then since in the last turn we had studied decision tree and random forest, so we have also used decision tree using entropy. And the standard process in a decision tree is to decide the depth of the tree. And all that has been done in a way that was explained last time. All the steps are standard. So now and here, instead of explicitly doing a train test split, k-fold cross validation has been used and the model has been built. So 7 folds have been used, and then we have tried to see what is the performance, and at a depth of probably 9, the training and test accuracies or performance are coming to be optimally best. We have chosen that. So that will be the depth of the tree. Using that, decision tree has been built. Then finally, random forest has also been modeled on the same data. And then again, in decision tree also, integer encoding and one hot encoding has been used. In random forest also, integer encoding and one hot encoding has been used. And then finally, all the results have been compared. So you can come to the final comparative, Ashish. And so these are all the models that we have built. 8 models have been used, which is KNN with integer coding, KNN with one hot encoding, naive Bayes with integer encoding, naive Bayes with one hot encoding, decision tree with integer encoding, decision tree with one hot encoding, then random forest with integer encoding, and random forest with one hot encoding. And then if you look at the different performance metrics, the models vary, in that aspect. For example, you can see that random forest with one hot encoding and integer encoding are parallel. Actually, naive Bayes and decision tree and random forest, if we talk about accuracy, overall accuracy, are quite parallel, and k nearest neighbor with one hot encoding is also giving roughly 82 or 83%. 82 or 83% accuracy. If we talk about precision, so the precision comes out to be highest for random forest, whether it is integer encoding, whether it is one hot encoding. If we talk about recall, then recall comes out to be best for naive Bayes one hot encoding and followed by one hot naive Bayes integer encoding. Then if we talk about F1 score, which is a balance over precision and recall, that comes out to be best for naive Bayes with one hot encoding. And then finally, if we talk about AUC ROC on the test data, then that comes out best for a naive Bayes with one hot encoding and random forest with integer and one hot encoding. So all in all, I think if we have to choose one model, then probably naive Bayes with one hot encoding more or less gives the best performance metrics for for all the values that are being analyzed. So this is mostly the flow of whatever we have done. Any quick questions on the flow, or shall we start with, I think Ashish can take you through the details of the data. Also, the entire flow of whatever is being done in the code has been provided in a doc file, which is there on LMS. And I think some of you had suggested that a block diagram would also help to explain the flow. So that is also included in that doc file. So you can have a look now or later as per your desire. So Ashish, with this, I'll request you to start going through the code in more details. Over to you.
Good morning, everyone. Am I audible to everyone?
Yes, Ashish.
Yes.
Thank you.
Morning.
Okay, here we go. So today we are working on adult census income data set. So it's basically a data set which contains demographic information from the 1994 US Census. And the goal here is to predict whether a person earns more than 50,000 per year or not based on various personal attributes captured in the data set. So, here we will provide the link of the data set. This is the page and the direct CSV link. I think it's not working. The direct link is down probably. It's not working today, but it's working fine till yesterday. Anyway, this is the page where you can, the whole website is down. So we have provided a data set in the file adult.data. You can use that. So this is the income, this is target variable income, which we have to predict, and it's a binary variable with values, with all the values either less than 50K or greater than 50K. These are the features, as we have discussed in various classes. We always mention their description. The data card should give the description of all the features, what are the data types and all. So we have a mix of categorical and numerical features. Now there is one particular feature I want to talk about, which we'll not be using. It's called final weight, FNLWGT here. So it's basically, it indicates, it's a sample weight, which indicates how many people a record represents in overall population. It was used by surveyors, but it is not a attribute of the person's income. It is not a specific attribute for predicting person's income. So we'll be dropping it from our columns. So all in all, there are 15 columns. So after dropping it, we'll be working on 14 columns. And from 14, one is our target variable income. So as always, we give a list of all the packages which we used. So from now, so it's like, it's the convention that we use, like pandas for loading the data set, the CSV files, matplotlib for plotting the graphs, all the data preprocessing, model building, and everything is under scikit-learn, where we have separate modules for preprocessing, for integer encoding, one-hot encoding, standard scaler for standardizing numerical features, discretizing, we have k-bins discretizer. For splitting the data set into train test, there are two different, which we have in last class, we have used train test split. I will show you the exact difference, how they are, these two varies, and k-fold, which we'll be using today. Now, there is k-neighbors classifier, which comes in the neighbors module. There is naive Bayes, and in naive Bayes, the particular variant which we are using is multinomial NB. And decision tree classifier, random forest classifier are from the old previous class. And like that, we have NumPy for doing mathematical operations. So what I wanted to start by showing is, let me show. So I opened the CSV, the adult.data file in Notepad. So what I wanted to show is when I do a normal read.csv. In earlier classes, I was just doing a pd.read CSV. PD is short for pandas. So it's a CSV file. I was doing a pd.read CSV and was just displaying the some rows of the data set, first 15 rows of the data set. What happens today is, even the first column, it comes as a row. There is no column header. Now this is specific to this data set, because the data set file which we have provided, how it is in the website. The website is maybe down today, but generally in the UCI data set, for this particular data set, they have not given any column header. It has been provided separately. These are just the raw numbers. So when we do a normal read CSV, we get something like this. So that's why today, for today's data set, which has some specific nuances, we first hard code the column names. These are all actually, when we go to the website page or download the overall data set, we have a separate file for the column names also. From there, I hard coded these column names. So we have to supply these column names, header equal to none, because this adult.dataset did not have any column header. And the names came from this column name list. Apart from this, there is skip initial space true. Now, specific to this dataset, there is a delimiter. This is a CSV file, so delimiter is comma, but after comma, there is a space. And this repeats for every feature. Like after comma, there is a space. So we tell it to skip after delimiter if there is any white space, then skip it. Apart from this, one more thing in this data set, if you can see, maybe it's not visible to me also. There are some column in the initial phase. Like if you guys can mark, I'm also seeing, if you guys can see any, okay, there it is. There is a question mark here. The missing values in this data set.
We cannot see your file.
Okay.
You have.
Oh, I'm so sorry. So I will just show here itself. So you can see this collab notebook. There's a question mark here. Can you see it?
Yeah, that we can see.
Okay, that you can see. So you can separately like open adult.data in a notepad, and you will see that these are comma separated values, but after each, after each comma, there's a space. Can you all confirm it? When you open adult.data in a notepad,
It is.
Yeah. So that's why I used a skip initial space equal to true here, and there is no column header. So I had explicitly given the column header, and the missing values here in this data set, they are represented by question mark. So to tell pandas that these are the missing values, we tell that missing values in the data set will be of the form question mark or a space or question mark. So that's why when I did not tell it, when I just did a pd.read CSV, it was giving a question mark. And for pandas, the question mark is not a missing value. Therefore, when I gave it these specific terms this time, so it is stating it is a NaN value, which it will treat as a standard missing value from now on. So is this thing clear? Because these are the particular nuances of the data set. So I thought it will be helpful if these things are made clear. Okay, I got a thumbs up. So, as usual, once we have the data set, it is in the variable df. We will do a df info over it to find out the data types of the various columns. And we can see, it is written 32561 entries, but for immediately we can see that for some entries there are only 30718 columns. For other, there are.
Sorry to interrupt you. So is these data is not having any specific? I mean, these are specific to a person related data, or it is random?
Like it's specific to a person. The age of the person, the working class, its education, marital status, education number, it's a numeric value, it's whether relationship, whether occupation. So these are like attributes of a person, and based on that, it's they have predicted what is their income. They have recorded the income, but it's less than 50K or greater than 50K.
When you say they don't have column, means like you're talking about the data we are receiving that is not containing, wherever like we can classify the column, like A is work class, based on the data we can divide, right?
So Mitra, Ashish, sorry to interrupt. Ashish wanted to say that the column headers were
this
not
header
available.
was not in initial file.
Okay.
There is not, this header is not there.
Yeah. So
in the
these
file,
have
the
been
header is
added.
not there.
Yeah.
Okay.
Yeah.
Okay, got it. Yeah. Thank you.
Yeah, thanks, Ashish.
Ashish, question is, suppose headers are not there and data is in the CSV, right? So in CSV, it is comma separated. Now, suppose someone is in some of the data, it might possible I miss the entire cell. Example, I miss the capital loss, which is 0, and it is not comma separated there. So how system will identify this is lost data for the that cell only?
Like what are you saying? In capital loss column, what is missing?
Instead of 15 column, suppose my data in the CSV, it is comma separated. It's 14 columns only.
Okay. So,
So is
like,
there any way?
No, there is no automatic way. Like, this is the initial part. We have to manually look at the data set first. And that's why we came to this conclusion that there are these things in the data set. There is like no automatic way that the function can do it for you. So if there are some missing values in data set, we have to initially make it, we have to clean it before even loading it. Like, these are the things, because it's a standard data set, we know that it's like lying like this, and that's why we apply these functions. And these are also like they have deliberately done this so that it's an exercise to tell people that in real life data sets, they can come in different shapes and size, and not all are ideal. So that's why these things were there in this data set. So like we have to see the data set in the Excel file and see manually see whether there are question mark and everything. Like, there is no automatic way to detect this thing.
Is it okay?
Yeah, thanks, Ashish.
Okay. So we proceed.
Yeah.
So after like seeing that there are some values are not like some values are 32561, some are less than that, we do a missing value per column check, and immediately we find that there are specific three columns which have missing values, other don't have any missing values. So what we do is we do a percentage, missing value percentage, or like how many values of the total samples are missing in each column. So it's 5% for work class and occupation, and for native country it's 1.79. Now, based on based on the domain expert or what is your requirement, like you can like if 5% is more to you, like if you don't want to drop anything, like then you have to go and fill these missing values with some imputation method. In our case, 30,000 samples are like 30, even after dropping them, we come to 30,000 samples, and even they are sufficient because the computation required here is much anyways. So we for simplicity also, and because of the computation also, we drop them. Now, this thing depends on the domain, like the domain expert decision. If 5% is like how much are you interested? If 5% is like it's tolerable to you to drop 5% of the values of this working class, then go ahead. Otherwise, do a imputation strategy. So after and here all and I like I told, I dropped the final weight column. It was not related to person's income, so I dropped that final weight column also. Okay. So after doing this, when I do now info on the data set name is now df_clean. Now I do a df.info. Every column has equal number of sample, equal number of count. And for sanity check, we do another missing value test. We do another missing values and see that there are no missing values in any column. Okay. After that, just for showing them, showing again that how it stores, what we are doing is like for df_clean, df_clean is the name of the data frame. When we do df_clean.columns, it will give me all the columns. And when I specify it that I want the object columns, because what we in pandas, the object columns are the categorical columns. So when we specify that we need the object columns, it will gives only the object columns. We store it in categorical columns variable, which is the categorical column. Similarly, when we do a select d type and specify that int and float columns are to be given, and we know these are the numerical columns, so we'll store it in a variable called numeric columns. Okay, so when we print them now, so there are 9 categorical columns, 5 numerical columns, or altogether 14 columns are there, in which 13 will be input and 1 is the target variable input. Okay, So this is the like unique values for each categorical column. Some have smaller unique values, like for work class there are only 7. For education there are 16 unique values, 16 categories we can say. For occupation there are 14 categories. Then native country there are 41 unique, like 41 categories. So like that, we have shown the count for each of the unique values. We always see the count plot for the target variable because it shows us whether the data set is imbalanced or not, and it's important. So we see that here 75% of the classes belong to, we can say, less than 50K or zero class, or greater than 50K only 24, or roughly 25% of the classes belong to the class 1 or greater than 50K. So this immediately shows us that classifying here is will be challenging because it is heavily tilted. Samples are heavily tilted towards one class. So the learning will be we can like have a we can have a initial conclusion also that the learning will be difficult because samples are heavily tilted toward one class. Okay. So today we are first we are focusing on the split. Ma'am told the cross validation split and how it is different from the train test split. So usually, I think I have okay. So I have it here also. So usually before this, what was happening was we were doing a train test split. So the main code is here, train test split. We were using a sklearn function train test split. We were giving it x and y's. We were telling it a test size, how much size we want the test set to be, and we'll specifying a random state which could be any. And I will come to what is stratify a bit. So what we were doing was we were doing a single split.
Sorry, I have Ashish one question. Like, why we are taking this random state? What is the purpose of this?
So random state is the purpose of random state is the reproducibility of result. So I'm just getting a bit forward. So these values which we get, like here, these values are there. So when you will do the experiment, you will get the same values because of the random state, the same split has been taken in your code also, and these values will be reproduced. If you take some other random state, so there will be some other values. So basically the split is 80-20, right?
Yeah.
So but what will be 20% and what will be 80%? It can vary. So like I can select first 80% as like if there are 100 samples, I can select first 80 as 80% and remaining as 20%. But you can select any other split also. Like you select the you start from the last thing and you select only the first 20% as a 20%. So you get this.
Okay.
So by random state, we are fixing that thing that it will always split the same way. How many times we run the code, it will always split the same way.
Okay, is it mean like that much percentage you have to select as a random value and rest of you select straightforward?
So Sunil, let me add here that basically this random state is done. It's kind of a seed value which is given as an input to the function so that the subset of the data that is chosen is always the same. For example, if I give you 100 records and I say that you choose 20 out of them, right? You can choose any 20, right? You can start from 1 and go up to 20 out of the 100 and choose these 20 and then use this as your test data. Suppose I ask Ashish to choose 20% as the test data. He can start from 80 and go up to 100 and then choose these 20 as the test data. Maybe someone else can choose 40 to 60 as the 20 number of samples 20. So because the train samples are varying, right? Every time anyone can choose, let's say if I have decided to choose 20 samples out of 100 as the test data, anyone can choose in so many ways. And depending on those different variations, though the results more or less will be same, but the actual figures may vary. Now what happens, today you have some results and tomorrow you want to report these results to your manager and the numbers change. Why? Because every time the system also, when you run the model, it will choose some particular set of samples, right? It can choose randomly any sample. So we want the results to be the same, right? So that you can reproduce them, you can, put them somewhere, so that the system gets a seed value. Based on that seed value, it's going to pick up certain set of records only as the test set all the time. So no matter how many times you run, the same set of records will be chosen as the test set, and the same rest of them will be chosen as the training set, and all the performance or any other analysis you do on that data will be same. So that's the reason for giving this. If you don't give it, I think this data is a little bigger. Otherwise, we could have just removed and showed you also that if you don't do it, then the results will change. They may not change substantially, but some changes will be there. Is it okay, Sunil?
Okay. Okay, ma'am. Yeah, okay, ma'am. Got it. And what is this stratify parameter?
I'm telling you what is stratifier now.
Okay.
Okay. So the last parameter which was there in trend test split is stratify. So what is, remember I told you that the distribution of the class level, the target level is 75-24 in the original data set. So even in the trend test split, after even trend test split, we want that the ratio should be intact. That's why we tell it that stratify according to the yth variable, which is the target variable. So when we do it this thing and I print it, so we see that now these YTR, YTrain and YTS, the train test split, which we obtained, they are I have shown for YTR. Similarly, I can show for YTS also. So we see that proportion is same. The proportion of class label is same in the train test data also. So that's why we use stratify. So see for test for the test Y the Y labels which are in test set, they are also having same proportion. The test labels which are in train set, they are also in same proportion, and it's roughly like same from the original distribution. So that's why we use stratify. So is it okay? Okay, so I continue forward. So this was train test split. The one major disadvantage with train test split was that it was arbitrarily fixing some split and dividing based on that this will be 80% and this will be 20%. Now the problem can arise that some easy samples can go that once we have fixed something as 20%, then they will never appear in train set, the test sets. And the 80% the train set, it will never appear in test set because these are mutually exclusive. Now the problem is the goodness of this is affected by the goodness of the split. So because of the random chance that something can occur in a train or test set, the results can be unreliable or sometimes biased. So what we do is a cross validation where we split the data into k equal parts. So from k equal parts, when we have split the data into k equal parts, the k minus 1 parts will be used as a train set, and the last 1 part will be used as test set, and we do this k times. So every fold, every fold will be getting a chance to become a test set, and everyone will get a chance to become train set. So these are more reliable results as compared to a single train test split. So that's why we use cross validation. And here also we use a stratified k fold to maintain the class distribution to the original data set. So that's why we use a specific stratified k. So this is a large code. So okay, the code starts from here, but I will show you what does there is in stratified k fold. So I've been commenting on the train test split because we have already explained this. So okay, so this is like for x, first we are making x's and y's. We are making x's and y's separate from the df clean because there is income column in df clean which represents the target variable. We remove it, and apart from this, every other thing is x, and y is the df income column. We map it because these are string values originally less than 50k, less than equal to 50k, greater than 50k. So we map it to 1 and 0. Okay. Then what we do is, suppose we had chosen a fold of 7.
Sorry to interrupt, Ashish. I hope all of you are following. If you find Ashish a little fast, you can just let us know now. Is it okay? The pace, I think he's just telling about the code, so because it's a bigger code. Is it okay, everyone?
Yeah, so far okay, ma'am. Maybe we will prompt if it is fast.
Okay. Okay, Ashish, then you can proceed. Thank you.
Okay. So, so we are telling like the difference between train test split and normal stratified K-fold. So we are on stratified K-fold. So these are the X's and Y. Like the same thing, we first had to make the X and Y, and even in train test split, we were given it X and Y. So now I am focusing on stratified K-fold. So we tell it the number of folds which we want. It can be 3, 5, 7, whatever, like whatever, for even the even numbers. We tell it that. Shuffle. Before the split, we want the data set to have a good a random shuffle, so that there is any chance of bias also, that it reduces. And as again, there is a random state here also. So this is a splitter object which has been created, the stratified K-fold splitter object KF. So what it does, it takes in X's and Y's in it, and what it gives is specifically what it gives is, it gives you the indexes of what will be the train data and what will be the test data. So like I have like printed them, this part of code. So train IDX and test IDX. So like there were so there are 25,000 based on 7-fold data set. We had used a 7-fold. So the 6 folds are used in training and 1 fold is used in testing. So these are the indexes of the 6-fold which will be used in training. And 4309 is the length of the indexes which will be used, the last fold which will be used for testing. So kf.split, it basically gives you indexes from the overall data set which will be used for train and which will be used for test. So this is how, once we get the indexes, we access these indexes from the data set X and Y. I think electricity has gone. Am I audible? Let's see.
Ashish, you are audible.
Yeah, I am audible, but I can be disconnected anytime. So that's why I'm telling. I will anyway join because it's a 1-2 minute power breakup. So okay, so this is how the indexes are available. So, okay, so this is how the indexes are available. Okay, so this is the part of how to get the how the
Ashish,
stratified.
question.
Yes.
So here you can see 4,309 is the test data, right? But in programming, where you mentioned these are the test data, number of test data is there. So it's randomly select, or
no, I could not get you.
7%.
Where is 4,000? I could not get you.
Your print statement, right? Train IDX, train IDX, test IDX, then length IDX.
These are indexes. These are indexes.
Last one.
This one.
Ashish, the last index is
okay. This is length. Yeah. This is length. These are okay. So 4 things are printed. IDX, which is a list. Test IDX, which is a list.
Yes.
Then this is the length. This is the length of the train IDX. This is the length of the test IDX.
Yeah, but how your system has decided 4,309 is the test IDX?
So I told you that we have told it to do a 7-fold split. So accordingly, 6 folds are in the train IDX, and the last fold, 1 fold is in test IDX.
Let me add here, there are around 30,100 something records. So you divide it by 7. So you get 4,000 something per fold. Right. So first 6 folds are your training folds. And the last one is your test fold, which is the length of 1 fold, which is shown here, 4,309. Stop.
Okay, so we are good to go?
Yeah, Ashish.
Okay. So this I specified in particular because we were using train test, we are using stratified today. So that's it. Now, if we want to, how to get this optimal fold. So we will have to loop in and see for all the values, some particular values. So we have like tested today for 3, 4, 5, 6, 7. We loop through these values. So this is the for loop for that, for looping through it. The internal code is the same stratified K-fold. Now, once we get the train and test data based on the stratified folds, we will do is because there are categorical columns and there are numeric features, what we'll do is we'll do a integer encoding, and for numeric features we'll do a standard scalar transformation to bring all the features in the range 0 to 1, mean 0 and variance 1. So this is the ordinal encoder, which is the integer encoding which we use. So it has one specific internal attribute to it, which is known as, which is written handle unknown equal to use encoded value. So what happens is, so suppose, because we are doing 7-fold validation, like suppose in training set we get 6 categories for a particular feature. Now in test set, apart from these 6 categories, another new category appears in the test set. So it's telling it to ignore it and give it a value -1. That's why we have particularly specified it. Otherwise, it will give a value error if it sees an unseen category during the test time. Other than that, there is a standard scalar, which will be used for transforming the numeric features. So for all our categorical columns, like I've done now this multiple times. So this categorical column we have stored in this variable, and numerical columns in this variable. So for all the categorical columns, the encoder does a fit transform. So basically for the trained data set, and there is only transform for the test data set. So basically the encoding which we want to learn is, we want to learn it on the trained data set. So that's why fit is usually performed on the train set, and the transform is actually where the actual mapping happens. During fit, it learns that these are your categorical variables and what will be the mapping, and the actual mapping happens during transform. So therefore, for the trained set, it is doing a fit transform. For test set, it is only doing a transform. Because it has already learned what will be the mapping, it just now transforms them. Similarly, for the standard scalar also, it does a fit transform to for each column. It has to learn in the standard scalar. For each column, it has to learn a mean and variance. So for learning them, the fit is performed on the train set. These are the train set, and the transform, once it has learned the mean and variance, it will do the transform accordingly. So for train set, for the train data set, we are doing a fit transform. For the test set, we are only doing a transform. So like this, we obtain our data set, which is now good to go for the inside the model, which is good to go for the model. Once we have this, now first we are trying to get the like the optimal number of split. So and that we are starting with k-near neighbor classifier. So this is our data prepared for KNN classifier. We give it a fixed value of k for now as 5. And all the other parameters are by default, which is that it uses Euclidean distance to calculate distances with other samples. These are by default, all the parameters are fixed in this library. Okay. So in sklearn, we always, the pattern is same for every model. You have to instantiate the model, then you do a fit over them. In fit, it's the way actual training happens. Now in specific case of KNN, the training is restricted to only storing these train values, because in KNN the actual stuff happens during the test time. During the train time, it basically just stores the training data, based on which it will do a nearest neighbor classification during test time. So there is a model.fit. Now, if it had been a decision tree classifier and we had done a model.fit, it would have created a specific tree from the train thing. Similarly, random forest would have created a tree. It had decided a split. So, but the function is common. You always do a model.fit, whatever is the initial classifier. Wait a minute. Let me finish this part. Then we can have a doubt session. Like there's not much. Okay, so once we have done this, we do a model.predict. So in the model.predict, we generally do for test data only, but I have done for both of them for plotting the graph. So model.predict, what it does, it gives you a specific class value for each of the input X train. For each of the input samples, it will give a class value 1 or 0 for each of the sample, whatever it has predicted based on the 5 neighbors. Similarly, for X test, it gives a class value. These are class labels, specific class labels, 1 or 0. Now, sometimes for plotting AUC curve, we want the probabilities, how much confident the sample is for that class. in k nearest neighbor, if there are 5 samples and like 3 samples based on its 3 nearest neighbor, it predicted 1 because they were saying 1. So there is 3 by 5, 0.6 by 0.6 probability. It has predicted that class is 1. So for these specific probabilities, we have a predict prob A in sklearn, which will give you probability. Now for now these things are standard for every model. We will see that even in naive Bayes, in decision tree, in random forest, we have these predict prob A, predict, and fit. These are specific to sklearn. These are standardized. Okay. Once we have this, we have our usual. In order to calculate accuracy, we can write our own function, or we just have to call sklearn function, which is accuracy score. It expects 2 values: the initial ground truth, the initial values, and the predicted values from the model for train, and this for test. Similarly, precision score, it also expects the same value. Just to ensure that the denominator is not 0, we give it 0 division. We give it a specific value to handle that. This is special attribute for that. And similarly, the same for recall, the same for F1. And for ROC, for AUC score, I told you that it expects probabilities. So you give it the ground truths, and you give it the probabilities which the model predicted each sample. So by this, this is the main thing which is repeated in all of the codes, and we store these values. Then there is a plotting. There's a function which is used to we store this value in a dictionary matrix k-fold, and then there is a function which access this dictionary and plots for us. So the thing is that because we are doing a 7, we are doing split of 3, 4, 5, 6, 7, and for for each of the split, model will be created for n number of time. Like for 3, there will be 3 models created. Like 4 split, there will be 4 models created. So the computation will take time. So I suggest if you not to run it right now. I ran in my local machine in Colab. It might take more than like 10 minutes. It can take to running this particular code. So this is a computation heavy code because there are 30,000 samples, and then we are looping. So the main problem comes because we are looping through it. We are looping through all the folds. So it takes some amount of time. It will not give result immediately. It will the code will take time. Okay. So these are the, then for each of the fold, we show the values. And as we told earlier, that 4 and 7 performed equally well, and we selected 7 so that we can average over more number of splits and get a better estimate of the overall performance. Okay, so by this we finish the stratified fold part. So we can so we continue forward or take questions.
I think you can take the questions. Sumitra, no, Sakshi followed by Sumitra, I guess. Sakshi.
Yeah. In the above section, like you shared, we'll be using different folds. It will be like 3, 5, 7. But for those folds, we are fixing the KNN, that is the nearest neighbor, that is 5. So will it change, like if we are changing the nearest neighbor value? Because
it can change.
Then how are we sure enough that the split that we are using is good enough for our data? Because we have randomly chosen the fixed number, then selected the best fold, like it should be 7, and then we are predicting the nearest neighbor again. How is it like?
So like it's a challenge. It's a like there is a no fixed answer to it. Like it's a challenging question for machine learning paradigm also. But this is just to have some starting point, because we don't know the split also. We don't know the fixed value of k also. But KNN value, like neighbor's value k equal to 5, it acts as a good starting point. Basically, we want to have some starting point. Like if you believe that there are some other split which can work well. So once we have find a good value of k, after that, when we choose for optimal value of k, then we can do it for that also. Apart from that, if you are like not sure you want to do for values of k and the split, so then we will have to do a 2-level code. So there will be two for loops. One will be iterate through all the folds, and in the other we will iterate through all the k values. So there will be 2 looping, and it will take more time. So if we have that computation power, Colab does not have that much computation power. Even in this, it was taking around more than 10 minutes. So that things like it's a trade-off of the computation power. If you
So,
had, we can do
yeah.
a 2-loop search also.
So Sakshi, the thing is that there are two things in it. One, that by some domain expertise, if you know that in your data what is the average density of points, then you can somewhat take a correct value of the number of nearest neighbors, right? There are two Ks in here. One K is the number of nearest neighbors, one is the number of folds. So we have to fix these two values to iterate and find out the one of these, the other needs to be fixed, right? So if you have some domain expertise, then you can fix some good value of the number of neighbors and then find out the optimal value of K. But if you don't have any idea about either of these, the number of folds and the number of nearest neighbors, then as Ashish was saying, you could have a loop over two variables in which you take a combination of these two, right? You take a combination of, let's say, number of folds 1, number of neighbors 1, then number of folds. So you'll have a double loop where you will loop over all possible values of the number of folds, and for each fold different values of k nearest neighbors, like that. So then that will be a very nice and foolproof thing, but that is possible only if you have the compute power to do so. In our case, we just have Colab at our hand, so it's not possible, but the
Yeah, I
ideal way.
understand, Ashish, I understand the code.
Okay.
No need to write
Okay.
it. Yeah. Okay,
So-
but another thing is, let us suppose I have the domain knowledge. How do I need to first then plot the data and then understand the density and decide for, some K value for the KNN? And
It's
folds
always-
I can set up like.
It's always good to do visualization, Sakshi.
Okay.
It's always good to do some EDA, visualize and see. And just even if you have some idea, then also this can help to validate that idea when you visualize the points and all that.
Okay. Okay.
Yeah. I think
Ma'am
Sumitra.
followed the same. Followed the same success question. Partially I got it, partial one. So now in this case, like we have the k value is 5, right? And I guess like what I understand, like we can have another also. So maybe like if I'm thinking, okay, 5 can be a k value and then 7 can be a 1. So should I mean, do we need to loop it in 5 for one analysis and again 7 for with another, and then we will verify like which one is going correct? Is that my
Yes.
understanding correct?
Correct. 100% correct.
Okay. One more question is related to the prediction. So I just wanted an understanding, like what is this predict and what is this predict probe? We define a prediction where as is stored, like we have y train pred and then we have
Ashish, you can take this.
Okay. So let me see if I could print them. If it's possible, so you see the predict, it gives you the actual binary values 1 or 0 for each of the samples, input samples. And when I do a predict prob A, it will give me probabilities value. So I told you the probabilities value in case of scalar is like if there are 5 neighbors and if 3 are saying 1, so probability is 0.6. So like that, it's calculating probability values. So probability values are required for doing the AUC curve. Otherwise, we just need the predicted values in the form of 1 and zeros. The specific probability values are required only during AUC curve. That's why we had it.
So the predict is just a 1 and 0 value. It's just a prediction 1 or 0.
Yeah, it's a hard prediction. So if I can show the first column says 1. So because for the 0th class it was having only 0.03, and for first class it's having 0.96. That's why it predicted 1. It's a hard value, and these are soft predictions in the form of probabilities.
Okay. Thank you.
So I think you can continue with the code, Ashish, from where we left.
Yeah. Okay. Just to inform you, electricity has gone again. It might got disconnected. Wi-Fi can get disconnected sometime. Okay. So we are now since we have decided the optimal fold, which is 7, now we will search for the optimal value of k in KNN. So this is the code for that. And now we are searching in the values 3 to 14 with the odd values in the range 3 to 14. So that's why I've used this. We have increased the step size is 2, so in order to get the odd values. Okay, so now since we have this time fixed the stratified fold, we have told it that n fold is 7, and the loop is over the k values. The same thing will be done as previously, but this time loop is over the k values. And first we are doing the integer encoding, like it is same as we done previously, the integer encoding, and standard scalar for numerical columns, integer encoding for categorical columns. Integer encoding in sklearn, it's by the function ordinal encoder. The same thing, model.fit, model.predict, everything is same. These are values, and finally we get the graph. And we can see in KNN, the things get like opposite. For lower values of k, there is a much difference in train and test. So this shows that for lower values of k, there are chance of overfitting, and for higher values of k, there are chance of underfitting in KNN. So to have a good value, we selected k equal to 11. Like we could have tried for other values also. If you wish, you could try. But for a good value for was to set it k equal to 11 here. So this is how we arrive at k equal to 11 for our work. Now, once we have fixed k value is 1, we'll do a final model evaluation. Till now we were just looping through various values. We will do a final evaluation with integer encoding for categorical features, and there is always standard scalar for numerical features, and these are the results. And also the split is in all this notebook. We are doing a 7-fold cross-validation split across all the models now. So these are the results for that, and it gives a very good result for the KNN. The drop is not that much, and all other values are also really a good number in this KNN. Then similarly, right now we were doing ordinal encoding. Similarly, now what we do is we do one-hot encoding of categorical features, like we have discussed in earlier classes. In one-hot encoding, for if there are 4 categories, there are 4 binary variables created for each category separately. So we do the same code. We loop. We first try to find that if there is some other value of k which can work good in one-hot encoding when categorical features are one-hot encoded. But we find that again k equal to, we settled at k equal to 11. It was giving a decent performance. Before that, like in recall, it's the highest. In all others, it's highest or the second highest, like that. So once we have done this, we do the one-hot encoding. So for one-hot encoder, again, when we one-hot encode the categorical features, we have this command. So it tells us that handle unknown equal to ignore. So basically, if there is some category which is not there in test, which is there in trainer and not in test set, so for that it chooses to put a 0 over it. So that is the particular attribute for it. And sparse output false. Basically, what we want is we want rows like this, 0 and 1s. The model automatically does not give them because it takes some storage space to give this overall sparse matrix. Sparse because most of the columns are zeros and only the place where the category is present is 1. So when we do a one-hot encoding, many of the values become 0. So like there are, if a category has 14 unique values, but for each sample, only one of the value will be there. So now there are 14 binary attributes for that column. So in 13, there will be 0. And in one particular, there will be 1. So there will be a sparse matrix, but we want that sparse matrix for our model evaluation. So we have to explicitly tell the model that sparse output equal to false. Based on that, once we do this, there is same fit transform for the train set and only transform for the test set. And there is a standard scaler for the numeric features again, because we are working right now, we are still working in KNN. And this is how we arrive at this. And we see that slightly there is a better performance than normal integer encoding in one-hot encoding for this KNN thing. So these are the summed up values of the train performance. With this, we finish the KNN part.
I think you can continue with the
Okay,
naive
okay.
base and then take questions.
Okay. So then we move to naive base. So the naive base, the thing is in KNN, in naive base, all input features are expected to be either categorical or discrete, but we had certain numeric features also. So what we do is first we discretize the numeric features and obtain a new dataset DF discretized, in which all the numeric features are discretized in the form of the columns are now called bins, and each numeric features is belong to one of the groups. So since we took bins equal to 5, so there are 0 to 4. So each value is encoded into groups 0 to 4 based on quantile strategy. So like this was discussed in last class also, quantile strategy, the data set is first, the particular row is first arranged in ascending order, and bins is set to 5. That means there will be 20, each 20% of data will be called one group, and like that we assign it to each group. So this is DF discretized. Now we see these features, these are in the numbers form, but these are still in the form of, these categorical features are still in the form of numeric ones. In strings, in string form. The model expects us everything will be in numbers. So we do integer encoding over them. Once we do an integer encoding over them, and it looks like this. So there are 14 columns, and everything is converted into numbers, integer encoded. We can also just to show you some, we could also have done a one-hot encoding over these variables of these categorical variables. Then like work class, federal, government, for each of the category, there will be like it's federal, it's local, it's private. So for each of the category, there will be a separate binary variable, but columns increase drastically. Now there are 113 columns overall when we do a one-hot encoding. Okay, so we are at the ordinal encoding thing. So first, for categorical features, we did the ordinal encoding, and the numeric features, they were for the entire notebook now, for numeric features, they have been discretized. And we will vary the categorical features. One time we will do its ordinal encoding, integer encoding, and one time we'll do its one-hot encoding. So for the first part, when the categorical features are integer encoded, we do a multi-normal naive base. So again, this is the stratified fold. N folds is set to the value 7. This is the same KF splitter. Now we loop through it to get the indexes of what will be the train and test folds. And now earlier we were having KNN. Now this is the same way of instantiating. We are using a multi-normal NB. So in sklearn, the function is called multi-normal NB, which handles all the categorical, which expects all the categorical values. So otherwise it's the same naive base. It's called but the name is in sklearn is multi-normal NB. So then we have model.fit. So fit here in multi-normal naive base, it does these probability calculations. You might have gone through the particular formula of naive base. So the probabilities which are calculated for calculating the class prediction. So that fitting happens here based on the train data. So once we have that, we can we again have that predict, which will give us the binary labels. We have that predict prob A, which will give the probabilities. And similarly, we store all these values. We can use them to get accuracy, precision, and we store these values. So this is naive base performance when using a 7-fold, when using integer encoding. And see, the performance is very bad. I think it's the accuracy is the worst of all the cases. So it shows like integer encoding really doesn't work for naive Bayes. But when we do a one-hot encoding, the same thing again, but the categorical features are now one-hot encoded. The numeric features were intact, like we can't see, there are so many features we can't see them, but numeric features were the same discretized one. So now when we do a naive Bayes, again do a naive Bayes with one-hot encoded features, we see that the performance is now again increased. So that means that integer encoding really doesn't work for, it's not working for naive Bayes particularly. Maybe because of how the probability function it takes in values of probability. So like we can have a separate discussion how how it's working, but we can see that for all the functions, even after that, that this is an outlier. The naive Bayes integer is an outlier. Otherwise, all are performing around 80 or more. So this I wanted to focus. Okay, so this is naive Bayes with one-hot encoding. Then we did do a comparison of what all values we have obtained till now, KNN and naive Bayes on both encoding. Okay, so
I think probably you can take it up to the end, up to random forest, and then we can have questions.
Okay. So then we we had studied two previous classifiers. We have studied two classifiers previously, decision tree and random forest. So we tried you don't have to change much of the code, so you just have to change the classifier thing. The stratified fold is same. So we wanted to explore that how they performed on the data set. So here also, so in decision tree, like the main hyperparameter is like in KNN, we have to decide what will the value of the neighbors. In decision tree, we are interested in what will the value of the depth. So first we for the first it is let me wait a minute. So first we are doing the depth for integer encoded. We are doing where categorical features are integer encoded, and we try to find the depth. We see that after 6 there is 7, there is increase, there is 8, there is increase, 9 there is increase, and after that it kinds of decreases. There is one value here which shows some increase, but the gap between training and test is much, so we discard it, and we use depth equal to 9 as our depth, as our value of depth for further analysis. We fix at 9. So with depth value of 9, we do the model evaluation, and we get these values. So again, I'm focusing it again. The code is same. We have a stratified k-fold. This splitter takes in, it gives the train and test indexes when you give it an x's and y's. This time I have written as CLF, but otherwise it was written as like model. So the thing is same. You have decision tree classifier, you instantiate it, you tell it the max depth that you want the tree to go, you tell it the criteria, you give it the random state, and similarly there's a fit here. The fit is the part where actual training happens, the actual splitting happens. Then there is predict function, which will give you by labels, actual labels on the on your input features. Then there's probability function, which will give you a probabilities values, and we store all of these. We are storing to print them later on, the values. Similarly, when all features are one-hot encoded instead of integer encoded, we can again search for tree depth. We see this is 5, 6, 7, 8. We can see around 8 there is the depth is optimal. There are some values after that also depth is increasing, but the gap is too much between train and test accuracy. So we use depth equal to 8. We again do a similarly we do a like final decision tree with one-hot encoded features and depth 8, and all of this is under stratified k-fold. So the fold value is 7. So we get these results, and so the comparison of the results, what is obtained till now. And finally, at the random forest, we work with random forest. Now, because this notebook was getting too much longer, and there is problem of computation here also because the data set is large. So what we did was we did not, in previous class we searched for the optimal value of the maximum number of features, as you can remember, and the number of estimators. In random forest we search for those values, but this time whatever the library offers, like the sklearn random forest, it gives us some default values for so estimators, it gives us default values of 100, so we use it. And max features, it uses a square root of the total number of features, so we use it. We don't test for them. Like we like last time we could have tested for them also and see what worked optimal. So this time we use default values, and like we came, max step was 9 for integer encoded features. We use that only from the decision tree, and these are the results. And then when they were categorical features are 1 hot encoded, the max depth was set to 8, and rest everything is like same. And these are the results. And then there's a final comparison of what all results we get. So the thing to note is like the upper model, the newer models today, KNN and naive Bayes, they are having better recall value, and decision tree and particularly random forest, it's having a better precision value. So now it's up to the like domain expert what thing they can, what thing matters to them, high precision or high recall, because one of them is, there is a trade-off in both of them. Apart from that, the accuracy value is more or less same in everyone, like around 82 or more. But apart from this, naive Bayes integer encoding, where it's only 77. So with that, this finishes the notebook code of the notebook.
So, any questions on whatever we have discussed? As already I had indicated in the beginning that we had learned two new classifiers, that is k nearest neighbor and naive Bayes. And last time we had done two kinds of encoding, integer and one hot. So we used a combination of k nearest neighbor with both of these on categorical data, and naive Bayes both of these integer and one hot on the categorical attributes. And additionally, we also discussed how to choose the number of neighbors in KNN, and also how to choose the number of folds in k-fold cross-validation. And those number of folds are common to KNN, naive Bayes, decision tree, and random forest. Those are common. But the number of nearest neighbors are specific to KNN. And in naive Bayes, all we need is the categorical attributes and the normalized values of the numeric attributes. Then in decision tree, we need the discretized values of the numeric attributes and the categorical attributes. And again, random forest also requires similar to decision tree. And so we have a final comparative. So the idea was to see a complete analysis of whatever classifiers we have studied so far, to see what works. Any questions, anyone, on whatever we have discussed?
Ashish, can you go to the graphs where we picked k equal to 11? I just want to understand it, like how did we take k equal to 11? Because I see 5 or if you go there, maybe 7 was something I was seeing. Yeah.
7 was the number of nearest neighbors.
No, I'm in this only. I'm
Okay.
talking about the readings.
Okay.
So you're saying why did you not use 7 instead of like why we use 11?
Yeah, so let me tell you what I'm thinking. So here in the test, we are always seeing there is an increase in accuracy, or all the configurations are increasing, and in the trained data it is decreasing. Now, how we say that 11 is we picked 11 as a optimum value? Can you once again explain me that? Because anyways it is decreasing because it is increasing for test data and decreasing for train data. I mean, I just want to understand it again.
So, like, if we can contrast with decision tree, like in decision tree, what happens is when we increase depth, the train accuracy keeps on increasing, and test is the dip in test accuracy. But so what we called it in previous class also, that this shows overfitting, that it keeps on increasing, and there is a when test accuracy starts to show a dip, we say that it's an overfitting phase. The decision tree is in its overfitting phase. So similarly in KNN, the thing is opposite for lower values of Ks, because it is now relying on less number of neighbors.
You can go to the graphs, Ashish.
So I am at the graph now of the KNN. So for lower values of Ks, because it's relying on less number of neighbors, so for an unseen sample, it's not predicting that well. But when there are more number of neighbors, like 11, or we can say like 14, 11, after 11 there's 13, okay, maybe 13. So that's why for more number of neighbors, the estimate is good that on the unseen data set, and for the train thing, it starts to show a decrease.
I'll add here, Ashish.
Yeah.
So the thing is that let's take one by one. So you can stop at one particular graph. So yeah. So if we consider the training data, let's say, and you look at the, so I'll refer to the accuracy right now. It can be any performance metric. So what happens is, initially, when we look at the training data, as we discussed yesterday, that when the number of neighbors that we consider is less, then the model will be overfitted, right? So on the training data, the accuracy or precision, etc., they will be very high, because it is just looking at one neighbor and using it to decide. So the model will tend to be overfitted, and therefore you can point it on accuracy graph, Ashish. Initially, when the value of k number of neighbors is 3 or 2, the graph is showing a very high accuracy for the training data, right? And as the number of neighbors keep on increasing, the graph is, the accuracy is becoming a little more and more generalized. And then beyond a point, say beyond value of 9 and 10, it is just decreasing, because the number of neighbors have increased so much that the training data is overly generic. So we are tending towards underfitting, and the model is getting confused between both the classes. So initially, the training accuracy will be very high, because the number of neighbors are very less and the model is overfitted. As the number of neighbors are increased for the training data, the model gets more and more confused, because more number of samples are coming in the neighborhood, being considered in the neighborhood. And it's likely that when the number of samples are very high, equal number of samples of, if there are two classes, both of them get included. And so the training accuracy tends to fall. Now let's look at the test accuracy. Initially, because test data is unseen data. So you can point it out there, Ashish. So initially, when the number of neighbors are very less in the test data, what happens is that with the help of very less neighbors, the inference on the test data is not good. The performance is not good, because model is overfitted on the training data. You see the converse high amount of accuracy on the training data with a value of 3 or 2 for the number of neighbors. So initially at the start of the graph, you can show near the origin. Yeah, Ashish. So you see here the value of the test accuracy is very low, because the model is overfitted. So it's going to underperform on new data, right? It is overfitted only on the training data. As the number of neighbors are increased, what will happen is that the test performance will increase, because now it will have more number of samples to deduce the class label. And then beyond a point, what will happen? It will just plateau out. So you can see that beyond the value of something like 9 or 10, it's or 11, it's pretty much getting plateaued out in the test data graph. So you can show that there, Ashish. So adding more number of neighbors is not going to help. And beyond a point, if we extend it further, the test accuracy is also likely to fall, because then the model will get confused over the test data also. So this is how we decide where the model is overfitting, where it is underfitting, and we take something in between, right? So this is how we choose the value of the k nearest neighbors. In this case, somewhere around 11, because in that case, the test accuracy is of utmost importance, that is substantially high, and the train accuracy is also not very low. So we chose that value. Is it okay, Ashish?
Yes, ma'am, I understood it. Now I understood why this graph is like this.
Next, please. I think Venkat or Venki.
Yeah, hi ma'am. This is on no like a discretizer function, right? So this basically converts the values to certain bins, right? So once it is converted, is it possible to revert to the original values back in case if we need to visualize or analyze later?
No, you cannot, because you have generalized the values. Let's say I've got a value like 2, 3, 4, 5, and all of them are lying in bin 0. Then I've replaced, in a way, I've replaced those values by the bin ID. So you cannot get back the original values. You can get them back if you have stored the bin ID along with the original values in your data frame or somewhere. Then you can get it. But conceptually, no, you cannot.
Okay, yeah.
Any other question? Anyone?
Yeah, ma'am. Don't have a question, but I need help of Ashish. Ashish, I am trying to upload the CSV file, but I am not getting the path. So can you explain how? Because entire program is based on that.
Okay,
I'm
so
able to understand the program.
I working on Collab, right?
Yeah.
So actually the path which I'd given, I'd written also that set the path. It was because I was working on a local directory. So you give this particular thing, you load it here. You in Collab, you load your file. It will prompt you to load from the system. You load it in this session, and then set this part content adult data. So then it will load.
Okay. So from the file section, I have to load the data, and then I can see.
Yeah, first you have to load the adult.data file from going this over this icon. It will prompt you to upload. You upload this adult.data file, and then you give this content/adult data. Maybe even without this also it will work. So see, so yeah, it's working. Even if you give just adult.data, it will work. But it has to be here. It has to be in this session. It has to be uploaded from the local system.
Amya, you can ask.
Yeah, hi, ma'am. So I just wanted to understand, like for KNN, generally, I understood that distance is, the assumption is that all similar data points will belong to will be close by, right, in terms of distance.
Yes.
So
Yes.
with that assumption, if we have, like, say, a very highly imbalanced class, right, or highly imbalanced data classification within the data set, is that going to impact the model itself? Like, maybe there are like in the case of fraud, right, there may be very few data points in one class versus the other. So will KNN even be a good model to consider for those kind of use cases?
So in this case also, you can see, Ashish, can you please come to the overall comparative at the end that you had included? So in this case, you can see that the data is very much imbalanced. And here, yeah. So you can see that k nearest neighbor is not giving very good performance. So the point that you have raised is correct, because what happens is that one of the classes is a dominant class, so more number of samples are there. So the probability of having neighbors which are from that dominant class is high relatively, and therefore the model is likely to get confused and likely to predict that class only with higher probability. Therefore, k nearest neighbor may not be a good thing to choose when the data is quite imbalanced, and which is what you are seeing here also. And I told you earlier that probably random forest or naive with one hot encoding may be better options. However, we could also treat the imbalance in the data by methods like oversampling and undersampling. So in oversampling, what we do is that we try to increase the number of samples of the minority class so that it becomes equitable distribution of the classes. In undersampling, we try to reduce the number of samples of the dominant class again to make it a equitable distribution. So we'll take it probably in some of the future sessions. So we can do that and then use any method. Is it okay?
Got it, ma'am. Thank you. Yeah.
Yeah, Prashant, would you like to go next?
So, ma'am, just I'm thinking about how we can apply into the current scenario in my work life, solving any business problem. And let's suppose we applied all these models and we landed up on this matrix over here. So again, it is dependent on a man on a domain person, and he needs to decide on this one.
Correct.
So how we are solving the business problem, how we are going to solve the business problem, because again we have landed on a decision factor that okay, if I have to choose based on the recall or I have to choose based on the precision, and if I have to implement a CI/CD pipeline, means a continuous improvement and development kind of thing, where everything is automated, and I will put my data and it will give me the final answer. Again, I'm not able to reach the decision. For example, if I copy paste all this metrics, put it into the chat GPT, and I will ask which one is the best. He is going to ask me, he is going to provide me some details on the recommendation, something. So just thinking how we are going to solve the real life business problem
Yeah.
when we land up on this matrix.
Yeah. So the thing is, the first and very important thing is definitely domain expertise is required in any field, right? For example, in medical field, you can do something, you can make a software, but you cannot replace a doctor. Similarly, in business scenarios also, it is good to have domain expertise. But if you wish not to have a domain expert, or if the domain expert is not available, then you could actually, after doing the complete analysis, you can put something like thresholds. Let's say that you know that in your business scenario, X amount of accuracy is good enough, and so much of precision, so much of recall, all whatever thresholds you have, you can actually add some code to select that model that satisfies all those thresholds that you want your model to satisfy. So like that, you can fully automate. But of course, you will need to have an idea about whether to choose a model having high precision or to choose a model having high recall. I already told you in the previous classes what it means to have a high precision, what it means to have a high recall. So in one case, the false positives will be low, in the other case, false negatives will be low. So whatever is of importance to you, whether a low false positive rate is important or lower number of false negatives is important, accordingly you have to choose precision or recall. And then accordingly you can set your thresholds and fully automate this. That is one way.
Okay, ma'am. So is there any again? I was thinking, is there again algorithm on the top of it to identify these things? Means setting a threshold and it will
Yeah,
give me.
so you'll have to write extra code which will take as input these performance metrics, and then you'll have to do some code some thresholds, right? That okay, if precision is greater than some X percentage or recall is greater than or equal to this much, then choose the model. So like that, you'll have to write some extra code. It's not going to be some very difficult code. You already have these. You can put them in a data frame or whatever way in a matrix, and then choose the elements of the matrix and apply the thresholding on it, and then get the final model. Okay.
Okay, ma'am. Yeah, thank you.
Any other questions, anyone? But Prashant, it is definitely important to note that it's very difficult to have a very clear-cut answer on, on a fixed method how to choose the best model, because it purely depends on.
Then we are learning model, machine learning, so many algorithm. Then how we are close to solve the real life business problem? If this is not the case, means maybe it is out of the scope of the current discussion. I'm sorry. Just thinking how it is really being helpful for a person or a man or the humanity. Sorry.
Yeah, so yeah. See, the thing is that even though the performance metric you see here might look a little confusing in the sense that you are thinking that I cannot make a final conclusion of which model to choose. But remember that you will have some extra information, right? You might be knowing that, okay, accuracy is of importance to me, or precision is of importance, or recall is of importance. And with that background information, you can decide the model. But if you don't have these performance metrics with you, you really don't know. You cannot imagine yourself what naive Bayes with one hot encoding will look like, or naive Bayes with integer encoding, or decision tree random for whatever. What will be good or bad? Without these figures, you cannot decide anything. That is one thing. Secondly, even if we are doing a lot of machine learning algorithms, even if you have deep learning added to it, or you have more number of algorithms to it, still this is an open problem only, that how to decide which best model to use. So it's not because of this data. It is an open problem anyway. In any machine learning, deep learning modeling technique, there'll be n number of models. They'll be behaving certain fashion. You have to have some criteria to choose which one you want. But with all this information, it can help you to choose. If you don't have this information, you really can't do anything at all. You cannot imagine the result. That is the thing. Okay.
So this means a person need to be very careful, because it will it it could become disaster if there is a wrong decision, or
Yeah.
if it is a biased decision.
Yeah, you're exactly correct. And that's the reason we are showing all these models, and also explaining conceptually what it takes to, use a model, then what are the performances like and all that stuff. So you need to be very careful while choosing a model, because once you choose, then your entire system will be based on that only. So you're right in that. That's why we need all this analysis, so we can decide what to use.
Okay, thank you.
Yeah, just
Okay.
ma'am, I want to add on it
Yeah.
because we do have experience with this kind of thing. Generally, what we do is we rank order the performance measures. Say, for example, if you test accuracy, precision, right? We rank order it, and maybe we take it some aggregate measure for the model, like that.
Yeah, you can also have aggregation over the performance by giving them all similar weights, or you can give them
Yeah,
unequal amount of weight. That's why I said that you need to
yeah,
know what is more important, precision,
yeah,
recall,
yeah,
or whatever. Yeah,
yeah,
that's correct.
yeah.
Anyone else? Anything else you wanted to know?
So, I have a follow-up question to Venkat on this. Like, how do you determine these weights? Like you mentioned that you do a rank order, right? So, how do you determine these weights?
So, Venkat, do you want to take that question?
Yeah, actually, it depends on the business problem to problem. Generally, what we do is we consider all the measures should be like equal weightage kind of thing. Say, for example, if you look at the test accuracy, right, you rank order say maybe 1 to 7 kind of thing. test precision also like 1 to 7, then test recall also like that, then actually we count like say, sum of all these measures kind of thing, then you rank order the toppest one, actually the best model kind of thing. But some cases basically we look at the weightage, but the weightage depends on the business how actually they want to look at from the accuracy point of view. That way actually, but it is not like a fixed my approach kind of thing, weights and all. But usually we take the equal weightage for all these measures kind of.
Yeah,
Uh,
got it. Thank you.
Yeah, yeah.
So for all these, there is no fixed answer actually, and that's why we are showing this whole matrix kind of a thing here. It's very difficult to say that we can fix it like this. It purely depends on the data, what you want to do with the data, what is the problem at hand, and you might give equal weights to all, or you might actually really treat only precision important, or you might have recall more important. So all that you need to see. Any other questions? Anyone? So I think then, yeah, any question? Okay, then if we are done with the questions, then we can break for today. Have a very nice day. Have a nice Sunday. And we'll meet in the next weekend. Thank you. Bye-bye.
Thank you, ma'am.
Ma'am, yesterday you spoke about to decide on the assignment kind of thing.
Yes, Bridge Bhushan, I could not get your voice properly. It's breaking. Can you please repeat?
Ma'am, yesterday you told that we will decide on the assignment.
Yeah, so actually, yes. So I think one of the participants had requested that the assignment thing, the link for filling in information or be open for one more day for today. So if it is open for today, then we can discuss it next turn. But would you want to discuss it now? Then I can do it also.
No, all right, all right. We will discuss in upcoming session.
Yeah, so because we are going to keep the link open the entire day today, I request anyone who's interested to fill the information, please do that. And we'll discuss in the upcoming session on the next weekend. Okay.
Okay, thank you, ma'am.
Okay, thank you. Bye-bye. Thank you, Ashish.
Bye.